Sometimes we talk about the energy of orbitals and sometimes we talk about the energy of electrons. We're really saying the same thing. Remember that orbitals are modes of motion described by wave functions and represented by three-dimensional shapes that the waves move through. When an electron is in an orbital, it is simply moving according to that function. So orbital energy and electron energy are the same thing. Ranking the energy of orbitals is one of the more difficult things that general chemistry students do. This is in part because it's new for most students, but also because we have done 3 different comparisons. And it's really important to be careful to determine which comparison you're making. In the previous module, we talked about comparing 2 orbitals on the same atom. We used the rule of thumb that filled or partially filled sublevels are lower in energy than empty sublevels. That's why the electrons go there first. We could use the periodic table and the electron configuration to determine this. In this module, we are comparing orbitals on different atoms. More specifically, we looked at the same orbital on different atoms, and we looked at valence orbitals on different atoms. Let's review our conclusions. We start with orbital energy diagrams for lithium, containing 3 electrons, and sodium, containing 11 electrons. We have placed them side by side where the corresponding orbitals are at the same energy. But is that correct? Let's think about 1s on lithium versus 1s on sodium. The 1s electrons on a given atom may shield each other a little bit, but these electrons essentially feel the full nuclear charge, which is +3 on lithium, but +11 on sodium. Going back to Coulomb's law, we're dealing with opposite charges, negative electrons and positive nuclei. So as opposite charges get bigger, the energy gets lower. 1s on sodium should be at lower energy. So, we can redraw these with 1s of sodium at lower energy than 1s of lithium. Notice that in our drawing, we made the sublevels all equidistant apart. Is this right? Almost certainly not. When we discussed the Bohr model, we noted that the energy gaps between levels changed as we went from level to level. We also made the gaps in lithium the same as in sodium. Is that right? Probably not. The 2p and 3s sublevels would feel a different amount of shielding in the 2 atoms due to the different numbers of electrons. But with all of the imperfections in the drawing, we are still going to assume that in any comparison between the same orbitals in the 2 atoms, the sodium orbital will be at lower energy. In general, our picture is that as you go from one element to the next and continue to add protons to the nucleus, the entire manifold of orbitals goes down in energy, as shown here in elements 5 through 10. The other orbital comparison we made was between the valence orbitals on different atoms. In this case, we would be comparing the 2s on lithium with the 3s on sodium. Notice that in the drawing, the 3s on sodium is still higher energy than the 2s on lithium. Is that right? Don't just assume that because 3s comes after 2s on the periodic table that 3s is higher. That only works when comparing orbitals on the same atom. Because these are now different orbitals on different atoms, we need a different criterion. In this case, we will appeal to the size of the atoms. We know lithium is a smaller atom, so its valence electron is closer to the nucleus than the valence electron on sodium. Regardless of any shielding or effective nuclear charge, for this comparison, size is the primary factor. Again, based on Coulomb's law, electrons that are closer to the nucleus will be at lower energy. So our drawing is correct. 2s on lithium should be at lower energy than 3s on sodium. Notice that we are ending this module where we started. when we compare the same orbital on different atoms, we are going down the right-hand side of this diagram, as the charge on the nucleus is our criterion. When we compare valence orbitals on different atoms, we actually have a measure of their location, the atomic radius. So here, the size of the atom is the criterion.